In this video, we'll explore the concepts of covariance and correlation. Consider a motivating example. Shown here is the joint PDF of two continuous random variables, x and y. Notice that x and y both vary between roughly -4 and 4. Further, the bigger the x value, the bigger y tends to be. We also observe these trends in a corresponding contour plot for the joint PDF, as well as in a random sample of x and y values from this model. In general, these plots illustrate that not only do the outcomes of x and y vary, they covary. Mainly, y tends to linearly increase with x. That is, x and y are positively correlated. Consider another example. In this case, the joint PDF of x and y, the corresponding contour plot, and a random sample of x and y values illustrate that x and y both vary between roughly -4 and 4, and x and y covary. Specifically, y tends to linearly decrease with x. That is, x and y are negatively correlated. Consider a final example. In this case, the joint PDF of x and y, the corresponding contour plot, and a random sample of x and y values illustrate that though x and y both vary between roughly -4 and 4, they don't seem to covary. That is, x and y are uncorrelated. We don't see that as x increases, y increases, or that it decreases. To better understand the relationship between two variables x and y, we can measure their covariance. First, recall that the variances of x and y measure the marginal variation in x and y alone. For x, the variance is calculated by the expected squared distance of an x outcome from the mean ex. The variance of y is calculated similarly. Now, the covariance of x and y measures the degree to which x and y linearly covary. This covariance is calculated by the expected value of the product x minus ex, just as we saw in our variance of x, but then we multiply it by y minus ey. Thus, this product captures the relationship between x relative to its mean and y relative to its mean. Equivalently, and typically easier to calculate, the covariance between x and y is the expected value of the product xy minus the product of expected values ex and ey. By this definition, the covariance of x and y can be any real number, and though the scale of covariance depends upon the scales of x and y, here are some generalities. First, a positive covariance indicates that x and y have a positive linear association. A negative covariance indicates that x and y have a negative linear association. And a covariance equals 0 indicates that x and y do not covary. Specifically, they don't have any linear association. Consider an example. Let x and y have the following joint and marginal models, specified PDFs f of x, f of y, and fxy. The plot of this joint PDF, fxy, is shown at right. Now our goal is to calculate the covariance of x and y. First, since we're familiar with these pieces, we can start by calculating the expected values of x and y alone. To this end, the expected value of x is the weighted average of x with weights defined by the PDF of x, f of x. I encourage you to confirm that this weighted average comes out to 7/12. Similarly, the expected value of y is the weighted average of y with weights defined by the PDF of y, and this comes out to be 5/12. Next, consider the expected value of the product xy. Since this quantity depends upon both x and y, we can calculate its weighted average of xy using weights defined by the joint PDF fxy. We can then plug in the formula of the joint PDF and use handy brackets to help us focus on the inner integral with respect to x. To make this integral easier, we can expand the product here as x squared y minus xy squared plus xy. Integrating this function with respect to x for x from 0 to 1 produces 5/6y minus 1/2 y squared. Now you might want to pause your video to confirm that this is accurate. Finally, integrating this function with respect to y for y from 0 to 1 ends up producing 3/12. That is, we expect the product of x and y to be 3/12. We now have the pieces that we need to calculate the covariance of x and y. Plugging in the expected value of xy, 3/12, and the expected values of x and y, 7/12 and 5/12, the covariance between x and y shakes out to be 1 out of 144. Stepping back, the fact that the covariance is positive indicates that x and y are positively associated. That is, x tends to increase as y increases, and vice versa. But what does 1 out of 144 mean? Is it a big number or a small number? That is the positive association between x and y strong or is it weak? Now it's really hard to tell. The interpretation of covariance varies from context to context depending upon the scales of x and y. Luckily, we can standardize covariance measurements. To this end, the correlation of x and y measures the strength and direction of a linear relationship between x and y. It's calculated by dividing the covariance of x and y by the standard deviations of x and y. Scaling the covariance relative to the scales of x and y makes the correlation easier to interpret than covariance. Mainly, no matter the scales of x and y, the correlation is always between -1 and 1. At one extreme, a correlation of -1 indicates that x and y have a perfect negative linear association. At the other extreme, a correlation of 1 indicates that x and y have a perfect positive linear association. In the middle, a correlation of 0 indicates that x and y are uncorrelated. That is, x and y don't have any linear association. To close, let's reconsider the examples from the beginning of this video. The first pair of x and y variables has a strong positive correlation of 0.8. The second pair has a weak to moderate negative correlation of -0.4. And the final pair is uncorrelated. That is, x and y aren't at all linearly associated.